Most organizations think Microsoft Fabric made SQL optional. They are wrong. T-SQL didn't disappear, it just moved upstream into the part of your platform where cost audit findings and mysterious performance incidents are born. And the bill always arrives late. Every one of these failures shows up later as cloud spend, audit findings, or teams losing trust in the data. In the next hour, you're going to use T-SQL the way enterprises actually need it, to enforce intent, truth, security boundaries, and predictable compute so your modern stack doesn't drift into conditional chaos. The foundational misunderstanding: beyond select means beyond responsibility. Here's the foundational misunderstanding. People hear beyond select and assume it means beyond SQL, or worse, beyond responsibility. They start treating the relational layer as an optional interface you can bypass with notebooks, pipelines, or whatever the lake gives us. And then they act surprised when the system behaves like a system with no contract, because that's what you built. Beyond select doesn't mean fancy queries. It means the parts of T-SQL that define a relational system as a disciplined machine: schema, constraints, transactions, permissions, stored procedures, and planned behavior. The things that make data deterministic instead of negotiable. Most teams use T-SQL like it's a reporting tool. It isn't. It is a contract language. A relational contract has two properties. One, predictable shape. Tables have declared columns and types, not whatever showed up today. Two, enforceable rules. The system can reject invalid states, not just display them with a warning in some downstream dashboard. If you remember nothing else, remember this: modern platforms didn't remove the need for relational discipline. They amplified the consequences of not having it. Fabric, Synapse, and the rest of the modern data stack are abstraction layers. They optimize for convenience and throughput. They do not optimize for intent. Over time, your intent erodes unless you encode it into the data layer in a way the system can't ignore. And that's where entropy shows up. Data entropy is the default trajectory: increasing disorder, unpredictability, and disagreement about what's true. Research on data entropy describes the causes as inconsistent inputs, unstructured accumulation, customization, sprawl, and time-based decay. That's not academic poetry. That's a weekly incident pattern. Here's a concrete micro-example, because abstraction without pain is just a conference talk. A Fabric warehouse ingests semi-curated data from a lakehouse. The lakeside is schema on read, which sounds modern and flexible. But without an enforcement step, it becomes schema never. A column that used to be numeric arrives as a string. A date arrives in two formats. A key that used to be unique now has duplicates because a pipeline replayed a batch. Nothing fails, everything loads. Then Power BI inherits the garbage. Someone fixes it with DAX. Another person fixes it in Power Query. A third person filters it in a semantic model. Now you have three truths in one dataset. And the platform's only response is to keep executing. This is why the distinction matters. SQL engines do exactly what you ask, not what you meant. T-SQL is where you make meaning enforceable. With explicit schema constraints and validation gates, you can force the warehouse boundary to behave like a boundary. You can reject invalid rows. You can quarantine drift. You can stop bad data before it becomes a BI argument and an executive escalation. Modern platforms help by making it easy to connect everything to everything. Convenience tooling accelerates policy erosion. It reduces friction for doing the wrong thing at scale. Entropy loves low friction. And once entropy exists in your data layer, everything above it becomes probabilistic. Performance becomes probabilistic because the optimizer makes decisions based on statistics that no longer reflect reality. Security becomes probabilistic because teams lean on workspace roles and assume that implies least privilege at the data layer. Truth becomes probabilistic because logic gets duplicated across pipelines, reports, and apps. So no, beyond select doesn't mean you graduated from SQL. It means you're now responsible for the relational contract you previously outsourced to a DBA you no longer employ. That sounds harsh. It is not optional. And the next step is understanding how SQL actually executes your intent. Because the code you wrote is not the order the engine runs. That's where the first trap lives. How SQL actually runs your query: execution order is the trap. People write SQL in a comforting narrative order. Select what they want, from where they want it, and then they sprinkle in where, group by, order by, like seasoning. The engine does not share that sentimentality. SQL reads like English, but it executes like a compiler. And compilers don't care what you intended. They care what you actually specified and in what phase of the pipeline that specification can be applied. Here's the execution order you need in your head, because it explains 80% of why is this slow and 80% of why did this return that. From happens first, always, then where, then group by, then having, then select, including distinct, then order by, then top coding order and execution order are not the same thing. That distinction matters because you are probably trying to optimize in the wrong place. The top makes it faster fallacy is the simplest example. People slap top 100 on a query and expect it to stop early like a well-behaved loop. but top is a late-stage operator. The engine still has to form the row set that top is applied to. If that row set is expensive to build, top doesn't save you. It just hides the cost behind a smaller output. If you visualize the plan left to right, everything expensive happens before top. That's why filter early isn't a micro-optimization. It's an architectural principle. Where shapes the workload before joins, expand it, before aggregations, group it, before sorts, reorder it. And the dirty truth is that joins are multipliers. A join doesn't just combine tables. It combines work, it amplifies I/O, memory grants, and spill risk. And if you join first and filter later, you've built a bigger intermediate set than you ever needed, and then you pay to throw most of it away. This is also why people get burned by, but I filtered in the select. No, you projected columns in the select. That is not filtering rows. That's decoration after the expensive parts happened. The thing most people miss is that SQL has multiple kinds of filtering, and only some of them save you. Where filters rows before aggregation, that can reduce join inputs and reduce the number of rows that group or sort needs to touch. Having filters after aggregation, that means the engine still had to group first. Having can be correct and necessary, but it does not save upstream work. It discards results after the expensive grouping already happened. Distinct is another late-stage filter. It removes duplicates after the engine produced them. If duplicates are produced by a join explosion, distinct isn't a fix. It's a tax order by is usually the tax nobody budgets for. Sorting requires memory. When the engine can't sort in memory, it spills. And spills are not a little slower. They're a structural admission. You asked for an expensive operation and the system had to page it out. Now, do not misunderstand this as right-trick SQL. You don't optimize by gaming clause order. The optimizer can reorder and transform. You optimize by giving the engine predicates and join conditions that can actually be applied early. Saggable filters, correct keys, and a schema that makes cardinality predictable. Execution order is the trap because it exposes a deeper point. Your query text is not the truth. The plan is the truth. The text is your request. The plan is the platform's interpretation of your request under cost constraints, statistics, and available indexes. And if you're trying to govern a Fabric-era platform, you don't govern with intentions. You govern with what the engine will actually do when someone runs this 2,000 times an hour. Once you understand execution order, you stop guessing. You start verifying. And that moves us to the only honest artifact in the whole process, the execution plan. Execution plans are a governance instrument, not a performance toy. Most teams treat execution plans like a performance troubleshooting tool you open when something's already on fire. That's backwards. An execution plan is a governance artifact. It's the only place where the platform admits what it's going to do to your data and your compute when this query runs under load. Not your intent, not your naming conventions, not your architectural diagram. The plan. And once you're in Fabric or Synapse-style consumption models, what it does maps directly to cost, blast radius, and incident probability. A stable plan is predictable compute. An unstable plan is conditional chaos with a credit card attached. There are two categories of plan inspection that matter. The first is estimated plans, what the optimizer intends to do. The second is actual plans, what happened when the query ran, with real row counts, real time, and real spills. The gap between the two is where failures live. If you remember nothing else here, estimated plans are a hypothesis. Actual plans are evidence. Now here's the uncomfortable truth. The optimizer isn't trying to make your query fast. It's trying to make it cheap according to a cost model built on statistics. If those statistics are stale or skewed, the optimizer will confidently pick a plan that is wrong. Not maliciously, deterministically. So when you look at a plan, you're not hunting for one magic operator. You're reading a risk report. Start with the simplest red flag, scanned rows versus returned rows. If you're returning 500 rows but scanning millions, you didn't write a query. You wrote an I/O bill. This is one of the most reliable indicators of wasted work, and it's highlighted in general optimization guidance. The bigger the gap, the more room you have to improve by filtering earlier, indexing properly, or fixing non-saggable predicates. Next, full scans on large tables. A scan isn't always a bug. Sometimes a scan is cheaper than using a non-selective index. But in governance terms, a scan is a liability. It scales with table growth. If the table doubles, your cost profile doubles. That's not a performance problem. That's an architecture decision you failed to make explicit. Then look for expensive sorts. Order by and certain group by patterns force sorting, and sorting forces memory. When memory isn't available, you get spills. Spills are the platform telling you it had to page out intermediate results to disk because your workload exceeded the memory grant. And yes, in distributed systems, this can become a multiplier. A spill plus concurrency is where it was fine yesterday comes from. Joins are the next category of plan risk because joins define plan shape. The join algorithm isn't a style preference. A nested loop that looks harmless at 1,000 rows becomes catastrophic at 10 million. A hash join that behaves fine under steady distributions becomes a memory hog under skew. A merge join wants sorted inputs. If it doesn't get them, you pay for sorts before you even join. The plan tells you which path you're betting on. Now, why does the optimizer pick wrong in the real world? 3 reasons show up constantly: stale statistics, data skew, and parameter sensitivity. Stale stats make the optimizer hallucinate row counts. Skew makes average estimates useless. And parameter sensitivity means the first parameter value compiled becomes the lens through which every later execution is judged, even when the data distribution changes. That's why execution plans are governance, because they're cost forecasting. A plan you can't predict is a system you can't budget. It's also a system you can't reliably secure, because performance incidents force temporary exceptions, bigger capacities, broader permissions, emergency bypasses. Those are entropy generators. So the practice isn't tune queries sometimes. The practice is every enterprise-critical query and procedure must have an acceptable plan shape, not just correct results. Plans are acceptance criteria. And once you adopt that mindset, you can see the first enterprise failure mode clearly. In Fabric, entropy doesn't start in the warehouse. It starts upstream in the Lakehouse inputs you chose not to constrain. Case 1. Fabric entropy when Lakehouse inputs become warehouse liabilities. So let's make this real. A Fabric warehouse pulls data from a Lakehouse. The Lakehouse is where semi-curated data lands. Notebooks, Spark jobs, ingestion pipelines, good enough CSVs, and whatever the source system emitted this week. The warehouse is where the business expects truth, repeatable reporting, stable semantic models, and numbers that don't change because someone reprocessed a folder. Those two expectations collide. And the collision is predictable. The failure mode looks boring at first. The pipeline keeps running. Data keeps loading. Dashboards keep refreshing. Nobody gets paged. That's the trap. Because schema on read without enforcement turns into schema never, and then every downstream layer starts compensating. A column that used to be int arrives as envarchar because one source started sending NA. A date arrives as text because a connector changed. A key stops being unique because an incremental load replays a day. Nulls appear where nulls were previously impossible. The warehouse accepts it because you never told it not to. And then the bill arrives in the form of data quality work, which is always framed as analytics work because nobody wants to admit it's a system design omission. So Power BI gets defensive logic, coalesce everywhere, parsing functions everywhere, fixes in Power Query, and DAX measures that turn invalid states into so the visual doesn't break. The result is not just slower refresh. The result is institutional drift. Now, truth depends on which report you opened. This clicked for him after watching teams argue over 2 numbers that were both correct because they were both compensating for different slices of the same upstream disorder. That's not a reporting problem. That's a contract problem. Here's the T-SQL intervention. First, you treat the warehouse as a boundary, not a mirror. That means you land data into a staging shape that is explicit, and then you promote into a curated shape that is enforceable. Explicit schema is the start, typed columns, not we'll pass it later. And then constraints where they are appropriate, primary keys, when you actually mean uniqueness, check constraints for domain rules, and not null when the business rule is this can't be missing. And yes, people will say constraints slow ingest. What they mean is constraints prevent loading garbage at full speed. Good, that's the point. Next, you add a validation gate that is set-based, not row-by-row heroics. In T-SQL terms, a predictable pattern of queries that count and quarantine invalid rows before they enter the curated tables. If rows fail the gate, they go to a quarantine table with reason codes. The pipeline doesn't pretend the data is clean. It declares the failure explicitly. This is where execution plans and constraints do governance work, not dashboards. Because a dashboard can only describe chaos after it's already shipped. A constraint stops chaos at the boundary. A validation query makes the chaos measurable and actionable, and the payoff is larger than performance. It's cognitive load. When the warehouse enforces shape, the semantic model stops being a data repair shop. You remove defensive transforms, refresh becomes simpler, and the business stops building parallel definitions in DAX just to make it work. Now, do not take that as permission to slap constraints everywhere. This is design. The goal is to encode the rules that represent business invariance and audit expectations, not personal preferences. The other quiet win is operational. When you enforce schema and validate early, incidents become diagnosable. A pipeline fails with a known reason, not a mysterious downstream visual break. Data contracts become visible. Which source produced invalid values, when it started, and how much it impacted the datasets. So you don't just reduce defects, you reduce ambiguity, and ambiguity is what burns teams out. Now here's the deeper connection back to the theme. Fabric makes it easy to move data. It does not make it safe to move meaning. If you don't enforce meaning at the warehouse boundary, meaning leaks upward into every consumer tool. Power BI, Power Apps, Power Automate, ad hoc SQL, quick fixes in notebooks. That's entropy acceleration. So case 1 isn't about being strict for the sake of being strict. It's about restoring determinism. The warehouse accepts only valid states, rejects invalid states, and keeps the blast radius contained. And once you do that, something else becomes visible. When data is clean and shaped, performance problems stop being random. They become planned problems. And planned problems in cloud billing models are usually hiding inside plan instability. Case 2, parameter sniffing, your cloud bill's favorite feature. Now we hit the failure mode that looks like the platform is flaky, but it isn't. It's deterministic, and it's expensive. Parameter sniffing is your cloud bill's favorite feature because it converts stable workloads into cost spikes without changing a single line of application code. This isn't a SQL quirk, it's a cost predictability failure. Here's the context that produces it. You have a high concurrency workload. Maybe it's a data serving layer for Power BI queries, maybe it's an API feeding Power Apps, maybe it's an orchestration pipeline that calls stored procedures repeatedly. The pattern is always the same. One stored procedure, one predictable shape, and lots of executions per hour. And then the incident tickets arrive. Random slowdowns. It was fine yesterday. One run takes 2 seconds, the next takes 2 minutes. Compute spikes, capacity alarms, people blame Fabric, people blame the gateway, people blame the network. Nobody blames the plan. They should. Because what's happening is simple. SQL Server-style engines compile an execution plan using the parameter values they see at compile time, then cache and reuse that plan for later executions. If the first parameter values represent a selective case, the plan might favor index seeks and nested loops. If the first values represent a broad case, the plan might favor scans and hash joins. Both plans can be correct. Only one is survivable for the next parameter distribution. So the same procedure gets executed for customer ID ELS 12 and returns 50 rows, and then for customer ID ELS 5 and returns 5 million rows. The plan chosen for 50 rows gets reused for the 5 million row case, and the system doesn't fail politely. It burns CPU and memory until your capacity looks like a denial of service attack you're paying for. That is parameter sniffing in enterprise reality. The reason this matters in Fabric-era systems is that cost is no longer abstract. You aren't tuning for elegance, you're tuning for predictable spend and predictable incident surface. So what do you do with T-SQL? You have a few levers, and none of them are magical. They are trade-offs you choose deliberately. 1. You can force recompilation for the specific statement. Option, recompile, tells the engine, don't reuse a cached plan, compile a plan for the current parameter values. That can stabilize runtime per execution context, but it shifts cost into compilation overhead. And if the procedure runs constantly, you can turn CPU into your new bottleneck. It fixes the symptom. It can create a new one. 2, you can change how the optimizer sees the parameter by using local variables. That tends to produce a more generalized plan because the optimizer can't assume a specific value distribution at compile time. The upside is fewer extreme plan regressions. The downside is you might lose the hyper-optimized plan that was perfect for the common case. So you're trading peak performance for consistency. 3, you can control parameterization more deliberately. Split procedures, branch logic for known small versus large distributions, or use query patterns that avoid wildly different cardinalities on the same code path. This is where people stop treating stored procedures as a convenience wrapper and start treating them as an operating model. And yes, SQL Server 2022 introduces parameter-sensitive plan optimization in some contexts, where multiple plans can be cached for a single parameterized query. That's the engine admitting the problem exists, but you still don't outsource governance to a feature checkbox. You validate plan behavior under your workload. Here's the practical way to keep executives and architects aligned. Don't describe this as sometimes SQL gets confused. Describe it as our runtime is probabilistic because the plan cache is using the wrong historical sample. Then you attach the real risk. Probabilistic runtime becomes probabilistic cost, and probabilistic cost becomes emergency changes, and emergency changes become security debt. That's the loop. The win condition for this case isn't faster queries, it's stable queries. A stable plan shape means stable memory grants, stable I/O, stable concurrency behavior, fewer spills, fewer lock escalations, fewer 2 a.m. escalations where somebody suggests just scale up capacity as if that's a fix and not an admission. Once you enforce stability, the incident pattern changes. Instead of random slowness, you get deterministic bottlenecks you can address with indexing, statistics, or structural choices. And that's the point. T-SQL isn't here to make your query clever. It's here to make your system predictable under load. Now, once performance is probabilistic, the next thing that becomes probabilistic is security, because teams start granting access broadly to avoid breaking critical workloads. That's where the next failure mode lives. Security debt in Fabric. Always on. Security doesn't mean always correct. Now we need to talk about security because performance incidents don't just burn compute. They create panic. And panic creates exceptions. Exceptions are entropy generators. Security debt is how those exceptions become permanent. Most teams hear Fabric security is always on and translate that into security is handled. That translation is how audits get interesting. The research is clear on the baseline. Fabric SQL databases use Microsoft Entra ID authentication, not SQL authentication. data is encrypted in transit with TLS 1.2 and encrypted at rest with Microsoft managed keys. Those defaults matter because they erase entire categories of legacy failure, weak SQL logins, forgotten certificates, stale patching. You do not have to earn those wins. The platform gives them to you. But that's not the security contract you actually need. Always on security is posture. It is not intent. Intent is who can do what, to which data, under which conditions, and how you prove it later. This is the uncomfortable truth. This isn't a Fabric flaw. It's an abstraction boundary problem. Fabric has a dual control model. On one side, you have workspace roles and item permissions because Fabric is a SaaS platform and it needs collaboration primitives. On the other side, you have native T-SQL permissions and database roles because the data engine still speaks in schemas, objects, and grants. And the failure pattern is simple. Teams stop at workspace roles. They treat contributor or member as if it translates into least privilege at the data layer. It doesn't. Workspace roles decide who can access or manage the item. They don't define a data contract inside the item. They do not encode which schemas are writable, which tables are queryable, or which stored procedures are callable. Over time, the workspace becomes a convenience zone and the database becomes an open floor plan. That's how security becomes probabilistic. Because when a system has no internal boundaries, every new integration inherits broad access by default. A pipeline identity needs to load data, so it gets elevated. A Power BI semantic model needs to refresh, so it gets elevated. A Power App needs a view, so it gets elevated. And nobody walks the permissions back because the system still works and the next person doesn't want to be the one who breaks it. That is security dead, permission drift you can't justify anymore. Now add 2 platform realities from the research that you need to say out loud. First, Fabric's security model is evolving, but some enterprise features are not fully there yet. Specifically, auditing and customer-managed keys are not currently supported. If your compliance program expects database-native auditing trails or customer-managed encryption keys, you cannot hand-wave that away. You either design compensating controls, or you accept that your Fabric SQL estate has a compliance boundary you must manage explicitly. Second, Fabric integrates with Microsoft Purview for labels and protection policies in preview contexts. That's powerful for governance, but it does not replace database layer intent. Labels classify, policies constrain at a higher level. They do not magically design your schema boundaries or your execution rights. So where does T-SQL fit? T-SQL is where you create survivable least privilege. Not by training people, by making the platform refuse unsafe actions. In architectural terms, you use the database to turn allowed into possible. You define schemas that separate curated from staging. You grant read access to what consumers need and write access only to what pipeline identities own. You stop treating broad workspace membership as a data access strategy. Because the audit question is never, did you encrypt data? The audit question is, who had access to sensitive tables and why, and how do you prove it? Fabric will give you a secure baseline. It will not define your intent for you. And if you don't define it, the system defines it for you through accumulated shortcuts, broad grants, and forgotten exceptions. That's the part that passes audits, or fails them. Case 3, least privilege that survives reality. Case 3 is where security theory meets the thing that actually breaks it, integration. Not the attacker, not the 0-day, the integration. In the Microsoft ecosystem, the most common path into your data layer isn't a hacker. It's a well-meaning product team wiring Power Platform into analytics because someone asked for real-time and the service principal needed access yesterday. So the pattern shows up: Dataverse, Power Apps, Power Automate, maybe a custom API, all touching SQL services somewhere. Sometimes it's a direct SQL endpoint. Sometimes it's a warehouse feeding Power BI, which then feeds embedded experiences. The details change. The failure mode does not. A service principal gets broad access because it's easier. A workspace role gets assigned because we just need it to work. A pipeline identity gets elevated because it kept failing, and then nobody comes back to remove the permission because nobody wants to be the person who breaks production. That's not a people problem, that's a design omission. Least privilege only works when it survives reality, and reality is messy. People leave, ownership shifts, requirements grow, and every exception becomes permanent unless the system makes permanence painful. Here's the architectural move that changes the trajectory. Treat least privilege as schema design, not as a policy document. Start by separating the database into deliberate zones. At minimum, you want a staging zone, a curated zone, and an access zone. Those zones don't have to map to Fabric's workspace concepts. They have to map to intent. Staging is where ingestion lands. It is allowed to be ugly. It is not allowed to be widely readable. Curated is where truth lives. It is constrained. It is stable. It is what you defend. Access is how consumers see curated data, views, stored procedures, and explicitly granted interfaces. This is where you make the easy path, also the safe path. Now, the permissions model becomes simple, and simplicity is what survives. You grant write permissions only to the identities that load staging. You grant read permissions to curated only through controlled objects. And you deny everything else by default. Yes, deny by default, not because it's dramatic. Because default allow becomes default sprawl. The thing most organizations miss is that workspace RBAC and database permissions are not substitutes. Workspace roles can get someone into the room. T-SQL permissions decide which drawers they can open once they're inside. If you don't define the drawers, the entire room becomes one shared drawer. Now add the part that actually makes this work across Power Platform. Power Platform loves abstraction. Dataverse abstracts the data model. Power Apps abstracts access patterns. Connectors abstract authentication. And those abstractions are useful, but they leak at boundaries. Eventually, someone needs a view. Someone needs a dataset refresh. Someone needs a pipeline to write back. Those are boundary crossings. So you design for boundary crossings. Create roles that represent real consumers, reporting readers, automation writers, ingestion loaders, and admin operators. Then map those roles to schemas and objects with explicit grants. Do not grant broad table access when a view will do. A view is not just convenience, it's a contract. It constrains what columns are exposed. It constrains how joins occur. It constrains what the consumer can accidentally do. Stored procedures do the same for write paths. If an automation flow needs to submit records, don't give it table write. Give it an executable procedure that validates inputs and writes into the one intended target. You've just converted ability into permissioned intent. Now, some people will ask about row-level security and predicate-based access patterns. The concept is valid. Restrict rows, not just tables. But the rule stays the same. Encode the boundary in something enforceable, not in app layer promises. If the requirement is this identity can only see these customers, then the database layer must be the place where that restriction is true even when the app changes. And here's the operational payoff that executives actually care about. Once designed, this model doesn't require heroics to maintain, because the permissions become attached to roles, roles attached to schemas, and consumers attached to controlled objects. When a team changes, you swap role membership. You don't rewrite the world. When a new Power App appears, you give it the reporting role, not the keys to the warehouse. And the audit conversation stops being theatrical. Instead of, we think only these users had access, you can show the grants. You can show the schema boundaries. You can show deny by default posture. You can show that the workspace role wasn't the final control. That is least privilege that survives reality. And once you have survivable least privilege, the next failure mode becomes obvious. Even with clean data and tight access, truth still drifts when business logic gets duplicated across layers. Case 4, business logic drift, the quiet killer of modern data. Case 4 is the one nobody budgets for because it doesn't show up as a failed pipeline or a security alert. It shows up as a slow loss of trust. Business logic drift is what happens when the rules exist in 5 places, get changed in 1, and everyone keeps pretending they're still aligned. In the Microsoft ecosystem, drift is almost guaranteed because every layer is capable of helping. Power Apps can validate and transform. Power Automate can branch and enrich. Data flows can reshape. Notebooks can fix it. Power BI can redefine truth in measures. And ad hoc SQL will always exist because someone always needs an answer today. Each layer can be useful. Each layer is also an entropy generator. Here's the drift mechanic in enterprise reality. A business rule starts simple. Active customers are customers with a current contract. And then a report needs it, so someone implements it in DAX. Then an app needs it, so someone implements it in PowerFX. Then a pipeline needs it, so someone implements it in a transform step. Then a different team wants active to include trial contracts, so they change their version. And now truth becomes negotiable. No one intended to create multiple definitions. They just optimized for local delivery. The system accepted that behavior because the data layer didn't enforce a single definition. And the consequences are predictable. First, audit pain. When an auditor asks, how do you calculate this KPI? The honest answer becomes, it depends which report you opened. That's not governance, that's theater. Second, operational drag. Every time a rule changes, you have to hunt it across layers. You change the Power BI measure, but the Power App still filters the old way, or the pipeline still tags the old way. Now, the data doesn't reconcile, and you spend time in meetings arguing about which definition is correct instead of fixing the system. Third, performance decay. Logic duplicated across tools is rarely implemented with cost discipline. You see expensive transformations happening in refresh, in direct query-like paths, in semantic models, and in app calls. The platform doesn't collapse. It just gets slower and more expensive, quietly, until it becomes normal. This clicked for him the first time a team swore 2 reports were reading the same dataset, and they were, but one had a temporary DAX correction that became the official truth for 6 months. Nobody documented it, nobody owned it, everyone relied on it. That's drift. The T-SQL intervention is boring, and that's why it works. You centralize business logic in the data layer, views for read semantics, stored procedures for write semantics, and constraints where the rule is a true invariant. You encode the definition once and then you make every consumer depend on it. A view becomes a contract surface. It says this is what active customer means, this is what revenue includes, this is how we treat cancelled orders. And because it's a database object, it's versionable, testable, and inspectable. You can review changes, you can see dependencies, you can see what breaks if you change it. And yes, this is where people get nervous because they've seen the database as a dumping ground. That's the trade-off you acknowledge upfront. Central logic requires ownership. Without ownership, the database becomes a landfill of half-finished views, conflicting naming, and procedural sprawl. But the answer to that isn't keep logic everywhere. The answer is governance. Define the contract surfaces deliberately, document intent, and restrict who can change them. Because the alternative isn't freedom, the alternative is entropy. Now, the practical payoff is immediate. When logic lives in one place, Power BI becomes simpler. Power Apps become simpler. Pipelines become simpler. Your semantic model stops being a rewrite engine and goes back to being a consumption layer. You can still build tool-specific calculations, but the core definitions stop drifting. And here's the part most people miss. Centralizing logic doesn't just make the numbers consistent. It makes the system cheaper to change. A rule changes once, tests run once, consumers inherit once, you reduce the surface area of change, and the incident probability drops because you aren't changing 5 layers that can each fail differently. So if you're trying to build modern data systems that don't decay, you don't fight drift with documentation and training. You fight drift by forcing a single contract surface. And that contract surface is still annoyingly T-SQL. Now, once you centralize logic, you've created something valuable. And valuable things get used, which means you now have to keep them fast under load. That's where indexing and statistics stop being optional. Indexing, the shortcut nobody teaches, is the trade-off. Indexing is where a lot of teams finally admit the truth. They didn't have a performance problem, they had an access path problem. A table is just stored data. It has no opinion about how you'll ask for it later. Without an index, the engine often has one honest option: scan until it finds what you asked for. That works when you're small. It also works when you're desperate. It stops working the moment the system becomes popular. An index is a pre-built access path. It's the engine's way of not reading everything. You're giving the optimizer a structure it can use to locate rows without brute force. That's the shortcut part. The thing most people miss is the trade-off part. Indexes don't make data faster. They make certain questions cheaper by making other operations more expensive. Every index you add is an ongoing tax on writes, inserts, updates, deletes, merges. The system must maintain the index structure. And in a Fabric or Synapse-style environment, that tax turns into compute and latency just as reliably as a scan does. It's just easier to ignore because it's distributed across every write. So you don't index because it feels responsible. You index because the execution plan proves you're paying a bigger bill without it. Here's how to decide what to index without turning your database into a museum of abandoned performance fixes. Start with the predicates that shape your row count, columns in where. If users filter by customer id, date, status, region, whatever, those are the candidates. An index that aligns with common filters turns scan millions to return hundreds into seek a narrow range and stop. Next, join keys. Joins are multipliers, and join keys are where the multiplier gets weaponized. If you join fact sales to dim customer on customer key, and that key isn't indexed in a way the optimizer can exploit, you invite hash joins and big memory grants. Sometimes that's fine. Under concurrency, it becomes expensive. Then, group by and order by patterns. These often force sorts. A sort is a memory negotiation. If the engine can't sort in memory, it spills. Indexes can reduce or eliminate those sorts when the data is already in the needed order, or when the index can be used to stream the rows in a way that avoids a big intermediate sort. Now, the warning that needs to be said out loud: you can't index your way out of ambiguity. If your predicates are non-sargable, functions on columns, implicit conversions, mismatched types, the engine can't use the index efficiently even if it exists. You didn't misconfigure anything. You designed a query the optimizer can't exploit. And indexing doesn't excuse bad data shape. If you have skewed distributions, the optimizer might still choose a scan because the index isn't selective enough. That's not the engine being stupid. That's the engine telling you this index doesn't actually narrow the work. So the workflow is always the same. Write the query. Inspect the plan. Look for the wasted work. Scans, heavy sorts, big mismatches between scanned and returned rows. Only then decide whether an index meaningfully changes the plan shape. That's why indexing is evidence-driven governance, not a tuning hobby. And you also need to internalize a second uncomfortable truth. Some indexes are entropy generators. The classic pattern is index everything someone complained about. Over time, you get dozens of indexes, overlapping, half-used, never removed. Writes slow down, maintenance complexity rises, and the optimizer has more choices to evaluate. You've created architectural erosion through helpful changes. The safe posture is a simple rule. Add indexes only when you can name the workload they support and show the plan improvement. If the workload disappears, the index disappears. That's how you keep the system from drifting into a performance junk drawer. And once you adopt that posture, indexing becomes less emotional. It becomes part of the contract. You're not optimizing for the query in front of you. You're optimizing for the behavior of a system under load across time as data grows. Because that's the actual job. Now, when indexes aren't enough, when the plan still has to read too much, you're about to leave query tuning and enter storage level discipline. That's partitioning. Partitioning, storage level discipline for billion row reality. Partitioning exists because you can't optimize your way out of scale. At some point, the table is just too large, and every plan choice becomes a debate about how expensive the inevitable scan will be. This is the moment where people say, we already indexed it. And they did, and it helped. But the query still takes too long, or the workload falls over under concurrency because the engine still has to touch a massive amount of data to answer a simple question. That's what partitioning is for. Partitioning is not a performance trick. It is storage level discipline. You are telling the engine, this table is not one continuous ocean. It is a set of bounded segments, and most queries should only swim in one segment. The most practical model is time-based partitioning, because almost every enterprise dataset has a time axis, transaction date, event time, ingestion time, effective date. And most enterprise questions are time-bounded, whether people admit it or not. Last 7 days, this month, this quarter, since the last release. So you partition by time, and you make time a first-class part of the physical design. The reason this works is simple: partition elimination. If the predicate aligns with the partition key, the engine can ignore entire partitions. It doesn't scan faster, it scans less. And scanning less is the only tuning that actually scales. Now here's where most people mess up. They partition the table, but their queries don't filter on the partition key. Or worse, they wrap the partition key in a function, making the predicate non-sargable. Or they filter on a different date column that's close enough. The engine can't eliminate what you didn't target. Partitioning only pays off when your workload cooperates. That means you have to enforce an access pattern. The partition key must appear in predicates for the queries you care about. If you won't enforce that, partitioning becomes overhead with no benefit. This is also why partitioning is not just a database decision. It is an organizational decision. Once you partition a table, you've declared a policy, how data is physically organized, how it ages, how it gets archived, and how consumers are expected to ask questions. If a team refuses to filter by time, they are refusing to operate within the system's cost model. That distinction matters because partitioning has governance benefits that don't show up in a quick demo. First, predictable cost. If last 7 days reliably hits one partition instead of the entire table, you've turned a time bomb query into a bounded query. Second, operational hygiene. Partitions create natural lifecycle boundaries. If you need to drop old data, archive it, or rebuild indexes, you can do that per partition instead of treating the whole table like a fragile artifact. Third, performance stability under concurrency. When many queries hit recent partitions, you reduce contention on the entire storage footprint. You localize the pressure. But partitioning does not replace indexing. It complements it. Partitioning reduces the size of the haystack. Indexing helps you find the needle inside the smaller haystack. If you skip either, you get partial results. Either you prune partitions but still scan too much inside them, or you have an index that's great but still spans an ocean you didn't need to traverse. Now, the critical rule for partitioning in enterprise systems is alignment. Align the partition key with how the business asks questions. Align the partition grain with how data arrives and how it's retained, daily, weekly, monthly. Align the queries with the key and enforce that alignment through code review and through contract surfaces like views that already include the time predicate pattern. Because the moment you let consumers bypass that contract, you're back to chaos. One query touches one partition, another touches all partitions, and your capacity planning turns into superstition. So partitioning is the point where T-SQL as control surface stops being metaphor and becomes physical reality. You are designing the shape of work the platform is allowed to do. And if partitioning still isn't enough, if you have indexes, partitions, and disciplined predicates and the workload still fails, then you're not tuning SQL anymore. You're changing the system's shape. Structural redesign, when query tuning stops working. Here's the line you eventually hit. You tuned the query, you added the right indexes, you aligned partitions, you updated statistics, and the workload still fails. At that point, the database isn't misbehaving, it's obeying physics. The trigger conditions are consistent, the query plan is already reasonable. You're not doing something obviously stupid like scanning everything for no reason, but the data volume is too large, the concurrency is too high, or the access pattern is fundamentally incompatible with the structure you built. This is where most teams spiral into conditional chaos. More hints, more indexes, more retrees, more capacity. They keep tuning symptoms because redesign feels like failure. It isn't. Structural redesign is the moment you stop pretending the access pattern is unknown. Most data platforms drift because teams refuse to declare what gets accessed together. They want the freedom of a lake, the governance of a warehouse, and the cost profile of a demo. The system will happily take that deal. Your credit card will not. So the principle is blunt. Store together what is accessed together. That means you accept that physical design is policy. If most queries always slice by time and customer, you design for time and customer. If most queries need latest state, you design for latest state. If most consumers need pre-aggregated results, you build a table or a materialized structure that represents that. You stop asking every query to be a research project. Now, this is where the normalization debate shows up, usually with ideological heat and very little evidence. Normalization is not virtue. Denormalization is not laziness. They are trade-offs in a cost model. Normalization reduces redundancy and can enforce integrity through keys and relationships, but it forces joins at read time. Under heavy analytics workloads, those joins become multipliers. Denormalization reduces join cost by pre-combining data that is frequently accessed together, but it increases write cost and introduces the risk of drift if you don't enforce update logic. So the correct posture is not normalize everything or denormalize everything. The correct posture is normalize where you need integrity, denormalize where you need performance, and enforce both with contracts. This is why enterprise warehouses use patterns like curated fact tables with denormalized attributes for common dimensions. It's not because someone hates third normal form. It's because they understand the workload. And in Fabric era architectures, you also need to be honest about when you're not tuning SQL anymore. Sometimes the fix isn't inside the relational engine. Sometimes the fix is changing the execution model, using Spark-style processing for transformations that are inherently large-scale and batch-oriented, or moving specific workloads into distributed compute where parallelism is a first-class property. That's not a performance fix. That's a system shape change. Same data, different physics. But here's the key discipline. Don't let Spark exists become an excuse to avoid relational contracts. If the output becomes a warehouse table that powers reporting, it still needs enforceable shape, constraints where appropriate, and governed access paths. Otherwise, you've just moved entropy from one compute engine to another. This clicked for him during migrations where teams replaced a slow SQL transformation with a notebook, got a speed up, and then watched defects multiply because nobody enforced schema and validation at the boundary. They optimized runtime and destroyed determinism. That is not progress. So how do you know redesign is required? If performance depends on heroics, if costs scale non-linearly with growth, if every incident ends with "we'll add capacity for now," if the same logical question produces wildly different plan shapes depending on which way the query got written. Those are structural signals, not tuning signals. And the moment you accept that, the redesign conversation becomes sane. You start from access patterns and contracts, not from syntax. You design storage to match usage. You decide where to pre-compute. You decide what to cache. You decide what to materialize. You decide what the system is allowed to do at query time. Because query tuning is local optimization, structural redesign is governance. Statistics plus plan cache, deterministic systems become probabilistic when you stop feeding them truth. After structural redesign, most teams expect stability to be automatic. They got the shape right, they partitioned, they indexed, they tuned the query, and now they want to believe the system will just stay that way. It won't. Because the optimizer isn't a mind reader. It's a cost model operating on two inputs, statistics and plan reuse. When those inputs drift, your deterministic design becomes probabilistic runtime again. Same schema, same query, different behavior. That's not mystery, that's starvation. Statistics are the optimizer's worldview. They are not nice to have metadata. They are the engine's estimate of how many rows exist, how values are distributed, and how selective a predicate will be. That estimate drives everything: join choice, join order, memory grants, parallelism decisions, and whether an index is used at all. No stats, no truth. And the first way this breaks in enterprise is painfully predictable. The data changes, but the optimizer keeps believing the old story. A table that used to be evenly distributed becomes skewed because one region goes viral, one product explodes, one tenant becomes dominant, or a backfill inserts 6 months of history overnight. The query text didn't change. The data did. If the statistics don't reflect that, the engine will choose a plan for a world that no longer exists. That's how you get plan regressions with no deployment. Now layer in the second component, the plan cache. Plan reuse is a feature. It saves compilation cost, which is real CPU and latency, especially at scale. But plan reuse is also the mechanism that turns one historical sample into a policy decision for the next 1,000 executions. That's why parameter sensitivity exists, and it's why even fixed queries can drift back into instability when the workload changes. The plan cache is where yesterday's assumptions become today's incidents. Here's the enterprise pattern. A workload runs fine for months, then a seasonal shift hits, or a new integration goes live, or a data load pattern changes. The cached plan still exists, it still gets reused, and now it's wrong in a way that only shows up under concurrency. The system doesn't fail loudly, it just starts consuming more CPU per request. Then memory grants grow, then spills show up, then queues form, then someone scales capacity and calls it solved. That's not solved, that's a tax. So governance here is not watch dashboards and hope. Governance is feeding the optimizer truth and verifying that plan reuse still matches reality. This is where monitoring stops being optional. You need visibility into what's running, what's expensive, and what's changing. Dynamic management views and query store concepts exist for exactly this reason: to identify frequently executed, expensive queries, track plan changes over time, and correlate regressions with deployments, data shifts, or configuration changes. You're not looking for one slow query. You're looking for the small set of queries that dominate cumulative cost because they run constantly, and the plans that keep flipping because the optimizer can't form a stable decision with the information it has. And yes, the fix can be as boring as updating statistics. And that's why this section matters. Teams love heroic tuning. They hate maintenance. But if your statistics are stale, every other decision is compromised. If your plan cache is polluted with plans built on outdated distributions, you'll spend money debugging ghosts. So the operational rule is simple: treat statistics updates as policy, not as cleanup. You don't wait for an incident. You define maintenance that keeps the optimizer's worldview aligned with the data's reality, especially after heavy loads, backfills, or major distribution shifts. Then you validate with plans and runtime metrics that the system stayed deterministic, because the platform will always drift toward entropy. Your job is to keep feeding it truth. AI plus Copilot SQL, it writes queries, not contracts. Now we have to talk about the newest entropy accelerator, AI-generated SQL. Copilot can write a query in 5 seconds that would take a junior analyst an hour. That feels like progress. It is not automatically progress, because AI optimizes for one thing: it returns results that look plausible. It does not optimize for determinism under load, long-term maintainability, or governance intent. AI accelerates mistakes at scale. And the uncomfortable part is that most teams won't notice until the bill, the incident, or the audit arrives. A bad query doesn't always fail. It just quietly consumes more CPU than it should, or returns subtly incorrect joins, or introduces a new definition of truth that nobody reviewed. So the rule for AI in enterprise data systems is simple. AI can draft queries. Humans must enforce contracts. A contract means at least 3 things in this context: shape, access, and cost. Shape means the query respects explicit schemas, correct data types, and defined business rules. If a column is supposed to be numeric, you don't handle the dirty strings in the report. You fix the pipeline or quarantine the rows. If a relationship is supposed to be one-to-many, you don't let an accidental join duplicate rows and call it more granular. Access means the query only touches what the caller is allowed to see. AI will happily select from a base table because it exists. It doesn't know that the base table contains sensitive columns and the consumer is supposed to use a masked view. That's not malicious. It's ignorant. Cost means the query has an acceptable plan shape. And this is where the governance mindset you already built becomes the filter for AI output. The most common AI failure mode is non-sargable predicates. AI loves writing helpful expressions in where clauses, wrapping date columns in functions, doing implicit conversions, or comparing unlike types. The query still returns the right rows, so everyone ships it. But the optimizer can't use indexes effectively. Suddenly you have scans, sorts, and spills that scale with data growth. Another AI favorite is unnecessary joins. The model sees table names that look relevant and glues them together. The result set looks rich. It's also multiplied. One accidental join to a non-unique dimension can inflate row counts by orders of magnitude, and then every aggregate becomes wrong unless you detect it. And of course, there's the classic select star. It's convenient. It's also a silent contract violation. You're exporting columns you didn't intend to export, including future columns you haven't even added yet. That's how "we didn't know that field was exposed" becomes an audit conversation. So how do you use AI without letting it turn your warehouse into a casino? You set acceptance criteria. Not does it work? Does it have an acceptable plan? Use the plan as the gate. Estimated or actual, depending on environment and risk, but the principle stays the same. The plan is the truth source. Here are the rejection signals you enforce immediately. First, scanned rows versus returned rows. If the gap is massive, you reject it, not because you love tuning, because you refuse to approve an I/O bill disguised as a query. Second, full scans on large tables with no bounded predicate. If the query doesn't constrain time, tenant, customer, or partition key, you reject it. That query is a future incident. Third, expensive sorts and spills. If the plan shows large sorts, memory pressure, or spill warnings, you reject it until the query shape and indexes are justified. Under concurrency, that becomes capacity pain. Fourth, joins that change cardinality unexpectedly. If the join keys aren't explicit, if uniqueness assumptions aren't proven, you reject it. You don't allow "maybe it's fine" joins in production. Now the safe usage boundary. Let AI write the first draft, then you rewrite it into a contract surface, a view, a stored procedure, a validated transformation step with explicit columns, explicit predicates, and permissions that match the consumer. And you store the plan behavior as part of the review. This is the acceptable plan shape for this workload. That's the only way this scales, because if AI can create SQL instantly, your system can accumulate bad SQL instantly. And once that happens, the platform becomes probabilistic. Cost, performance, and truth all drift. So the promise of AI isn't that it replaces T-SQL. The promise is that it forces you to treat T-SQL like governance, not like typing C. The operating model, T-SQL as control surface. Here's the operating model, and it's the only one that survives contact with a real enterprise. The problem is never that you can't query data. The problem is that modern data platforms make it easy to ship ambiguity, ambiguous schemas, ambiguous definitions, ambiguous permissions, and ambiguous cost behavior. And ambiguity doesn't stay contained. It leaks outward into reports, apps, pipelines, and eventually into incident tickets and audit findings. The reason the current approach fails is because most teams treat SQL like a retrieval tool and governance like a separate discipline. They build modern stacks that move data quickly, but they don't enforce intent at the boundary where it matters. Then the platform behaves exactly as designed. It executes whatever you asked for, not what you meant. The better method is to treat T-SQL as a control surface, a place where you encode intent into enforcement so the system can't drift into randomness without tripping alarms. If you remember nothing else, remember these three invariants: enforce shape, enforce access, enforce cost. Enforce shape means you stop accepting, we'll fix it downstream. In practice, that means explicit schemas, typed columns, and constraints where business invariants exist. It means validation gates that quarantine bad rows instead of spreading them across every consumer. When shape is enforced, the warehouse stops being a rumor mill and becomes a contract. Enforce access means you stop confusing can open the workspace with can read the table. You use schemas, roles, and controlled surfaces, views, and stored procedures to make the safe path the easy path. You assign identities to roles and roles to objects, and you make broad access painful by design. Least privilege becomes a configuration reality, not a training outcome. Enforce cost means you stop treating performance as a late-stage tuning activity. You treat execution plans as risk signals, scanned versus returned rows, scans on large tables, expensive sorts, spills, unstable plan shapes under parameter variability. Cost predictability is not a nice-to-have in cloud platforms. It's the difference between a stable service and a weekly fire drill. Now here's the uncomfortable truth, where people regress. They regress at the first exception. A pipeline fails, so someone grants more access. A report breaks, so someone patches the DAX. A query runs slow, so someone scales capacity. A Copilot-generated query works, so someone deploys it. These are not fixes, they are entropy generators. And entropy generators accumulate. They don't announce themselves. They just change your system from deterministic to probabilistic, one temporary shortcut at a time. So the practical checklist mindset is this. Every change must declare intent at the data layer. If you add a new source, declare its schema and validation expectations. If you add a new consumer, declare its access boundary. If you add a new query pattern, declare its acceptable plan shape. If you can't declare those things, you don't have a design. You have hope. Fabric and Synapse give you powerful abstractions. Lakehouses, warehouses, notebooks, pipelines, direct lake, all of it. Useful, but abstraction is not governance. Architecturally, every layer you add increases the number of places truth can drift. So the control plane has to be enforced somewhere in these ecosystems. That somewhere is still the relational engine and the T-SQL surface area that defines what the system is allowed to do. That's why this episode is titled Beyond Select. Select is the easy part. The contract is the part that keeps your system from decaying. T-SQL isn't a querying language. It's the relational contract that keeps Fabric-era systems deterministic instead of drifting into entropy, cost spikes, and security debt. If you want the next layer, watch the episode on reading execution plans as risk signals. Subscribe. This channel assumes platforms decay unless governed.